In the previous video lecture, we created an R project. We opened this dog microbiome tutorial file and we sourced the custom functions that we're going to be using downstream. We've read in our taxonomy table and our ASV counts, and now we're going to create those user-friendly ASV IDs to replace the sequences that we get by default. So if we, just to remind you, look at that row names of ASVs, it gives us the sequences. And now we're going to use the paste 0 function, which does exactly what the name implies. It pastes two character vectors together. So we're going to start our ID with ASV, and we want 1 to the length of seeks. So the length of seeks, that would be 4,415 ASVs. So if we do this line and we have a look, then you'll see we get ASV 1, 2, 3 all the way to 4,415. So now we want to associate a given sequence with an ID. So we're going to take the ASV IDs and make a named vector with seeks that we previously created. So if we do that and we use head seeks, you'll see for each sequence we now have ASV 1, 2, so each of those sequences now have an ID. And we can also just record the number of base pairs in each sequence with the ncar function, and we'll save as seek_lengths, and that way we can just be aware of how long our ASVs actually were, and we can actually look at the distribution of the lengths of those ASVs. So it's always good to kind of really explore your data when you first import it and get a good feel for what it looks like. So we'll see the majority are 302 in length, with quite a few also being 312 and 313. So very similar. So now that we've done that, we're going to merge the ASV table and the taxonomic table into our fileseek object that we previously discussed. And we can do that with the fileseek function. And in fileseek there is also a function called OTU table and another one called tax table. So say we just look at tax table of our taxa. Okay, there we get the taxonomy table. It's still a bunch of sequences, but let's now merge that into a fileseek object. And again, just check that our taxonomy names between this fileseek object is the same as the row names for our ASV table, and it is. And now we can take our ASV IDs that we created, and we can actually assign it to taxonames phi. So currently the function taxonames phi will bring up the sequence IDs, and then we're just going to go and replace them with that named vector ASV IDs that we created. So let's look at the structure of this fileseek object that we made. So we previously discussed that the fileseek object has several slots denoted by that @. So you'll see we've got the OTU table and the taxonomy table that we've now imported, and then we still have 3 empty slots. So SAM data is your sample data, which we'll still import, and then phi_tree is a slot for your phylogenetic tree. So for this demonstration we won't be using a phyloseek tree, but bear in mind that if you do have a phylogenetic tree, that you can import it and join it to this fileseek object. So let's have a look at our taxonomy table. So if we separate that as a data frame from our fileseek object using the data.frame function, and we're going to assign it to something called tax_df, we can also add to that data frame with the dollar operator a column called seek_len. And those are the sequence links that we created previously. And if we do that, we can actually go into our environment here and we can look at that tax_df data frame by clicking on it, so we can get a better overview of our table. So now we see we've got those nice user-friendly ASV IDs that we created instead of the sequences, and we can see for each ASV we've got full taxonomic annotation from kingdom all the way to species level. So we won't have species level for each and every one, but we do have for the majority. And here is the seek_len column that we added, so we can also see the sequence length of each of these ASVs. And what I want to point out is that for several ASVs you'll find identical species level annotation. And if you actually go look at the underlying sequence, you'll be able to see there a handful, maybe even only one or two base pair changes between these ASVs, which is why they are separate entities. But downstream, we might want to merge all these identical species into one unit, which will make it easier for us to interpret the data. So let's see what proportion of ASVs did actually get species level annotation with different databases. So if we do is NA of this tax_df species, it'll tell us which of our ASVs had species level annotation. If we then add which and over that length, it'll tell us how many of those ASVs had species level annotation. So for 1367, is NA was true, and just to remind you, we had 4,415. So there were over 3,000 for which we actually had species. So over 70% with the RefSec RDP database had species level annotation, which is really good. If, for instance, for the same data set we'd use green genes, we would have had only 32% assigned to species level. So it's good to be aware of the different taxonomic databases, and I've also listed for you here on the H3O Bionet course website where you can find taxonomic reference databases that you can actually use with Data2. So for your own project, you can go have a look at this, and here are all the databases that are available to you. Okay, so if we next import our metadata, so we've got our count data, taxonomy data, now we want to add our sample data for downstream analysis. So that's that practice dataset metadata that you should have added to your r_downstream folder, and we can use the read.table function to import this TSV file, and we're going to specify sep is T, so this is a tab delimited file. We're going to tell it does have a header, and our first row has the names. So if we do that and assign it to something called meta, we can look at this metadata object, and you can see you've got your dog identifiers, and then you've got your dogs. So we've got dog B, G, and K, and then for each of those 3 dogs, we've got different treatments. So if you look at that full data set, there you can see the 15 different samples, different dogs, and the different treatments that each dog received for those samples. So before we join our metadata to our phyloseq object, we have to make sure that the sample IDs that we have in our phyloseq object already, so that would have come from your upstream data to processing, matches the sample names in your TSV or your CSV sheet that maybe a client gave to you. And it's often not matched, so you actually have to make sure that they are matched. You may have to do some tweaks. So if we look at sample names of the phyloseq object, and we can look at the length of both the phyloseq object and of the row names of our metadata object. In this case, we see they both have 15. And then we can use the intersect function to see that they are actually identical. So then we should have a length of 15 for that intersect as well. And in this case, we do. So once you're sure that that intersect between those two data sets are the same, you can go ahead and assign it to your phyloseq object, and phyloseq will put these in the right order. So all you have to do is take that meta, which is currently a data frame, and assign it to sample data, which is how you access that sample data slot in your phyloseq object. So if we look at that before, you'll see it tells you SAM data slot is empty. So now we can go ahead and do that assignment. And if you look at it again, you'll see now we have that nice sample data information in there. And just to double check, you can use identical on that sample names phi and check that it's the same as your column names of your OTU table. So where your column names are your sample identifiers, and in that case it's true. So now we revisit this phyloseq object, and now we can see we have a data frame, 15 observations, so 15 samples with 2 variables. And let's look at how this data was imported. So the first one you'll see is a factor variable. So remember we discussed the different structures in R. And then the second one is actually an integer. So in this case, the dog was saved as a factor variable, but treatment, because it's numbers, were saved as integers. But for our downstream analysis, we don't actually want to see treatment as numeric. It's actually just treatment 1, 2, 3, 4 as in categorical data. So because it's categorical, we want to convert the integers to a factor structure. So to do that, we're going to take the treatment column of our sample data phi, so just isolate that one column, which looks like that. And then we're going to use the as.factor function to convert that treatment object. But what we have to do first is use the unlist function just to extract that data from this object. And once we've done that, you can look at it again. And now you can see we've got 2 factor variables as we expect. So now we have our phyloseq object with everything that we need, and you can go ahead and save that as an RDS object with the save RDS function. So you specify the object name, which is phi, and then a name for the RDS file, and that will save in your project directory. If you need it at a later stage, you don't have to rerun this whole analyses. You can simply use the read RDS function to load that object from memory, and you'll have your phi object available to you. So that's it for our data import session. In the next video, we'll be exploring our data and doing some downstream analyses.